Okay, we're recording now. Just wanted to make sure of that. And let's repeat these advantages for purposes of the recording. What we've done is we've shown that the maximum MAs are very close to the set MAs, and that the maximum KVPs are very close to the average. So when you go to three-phase, your averages are very close to the maximums, and that's what gives these three advantages. You have an output advantage because since the waveform and voltage in MA doesn't go to zero with three-phase, well, then you have consistently higher MA and a consistently higher average energy. That means more output. That means less exposure time. That means less motion problems. Huge advantage of three-phase. The patient dose advantage comes about because your average energy is very close to your maximum energy. The average energy in single phase, the energy goes down to zero and at times. So average energy being low, that means then, let me put it on the positive side, average energy being high on the three-phase means better penetration because you have a higher average energy. And finally, heat capacity is greater since your average MA, which is the MA that you set, it does not the tube does not stress to very high MAs. The average MA is essentially equal to the maximum MA. There's only in a six-phase, three-phase 12 pulse, the variation between average and peaks is only 1.5% on either side of the average. Okay, so those are the three advantages of three-phase. Let's move on. Before the core exams, this was one of the favorite questions that they asked. Yeah, as far as I know, they haven't asked it on the core exam, but it is a conceptual question, and they may well ask it in the future. Let's do exactly what we were doing before, but this one is kind of different. 100 kV, 175 MA, what's your maximum time? Well, you go, as before, you go to the 100, you see where it crosses the 175, and this is where it's different. It doesn't cross the 175. You see the 175 down here? It doesn't cross the 175. So the choices that they have given on the boards is an extremely small amount, let's say 0.001. And a lot of residents would say, okay, it doesn't cross it, but okay, I'll give it the smallest. The idea is that if the KV does not cross the MA, then no amount of exposure is safe. No amount of exposure. No amount of exposure time. And the answer to this particular one is you cannot set those exposure settings of 100 and 175. Any time would blow up the tube. No time is safe. Okay? Okay. How do you calculate heat units? How do you calculate how much heat is produced at the anode? First of all, it's the heat unit, HU, that we use to specify amount of heat. And here you have the heat unit equals the running product of KVP, MA, and time. And it's approximately the energy. It's a measure of the energy produced for one exposure in units of joules. There is a slight difference, but for purposes of the boards, the heat unit is a measure of the energy produced for one exposure, and that one exposure has a particular KV, particular MA, particular time. And if you have multiple exposures, like if you had a rapid serial acquisition, and where you repeat the exposure over and over again, well, then you have to multiply that running product by N. How many exposures did you take? In that a serial acquisition. It's as if you had taken one big exposure and you just calculate the heat units there by just multiplying by the number of images. Here's a quick example. Find the heat units if you took a rapid serial acquisition run of 10 images for 100 kV and a 500 MA and a tenth of a second. Okay, well, it's just that running product multiplied by 10, N equals 10. And a quick little math there will show that this is 50,000 heat units. That's how you calculate the measure of heat that you produce when you have a particular exposure technique. Now here is a couple of other wrinkles on this. Remember we saw that in three-phase the average is much closer to the maximum and is almost the maximum. Well, that means that when you go to three-phase, for the same kVMA time settings, you produce more energy. And how much more energy? Well, these little nitty-gritty numbers, 1.35 for 6 pulse, 1.44 for 12 pulse. I don't think you have to remember the actual value of the number, but the idea, the concept. The concept is that when you take an exposure, you're going to produce heat. And how much heat you produce depends on your technique settings, kV, MA, and time. And it also determined by how many images you take in rapid serial succession. And now finally, it's also determined by its three-phase. Three-phase is so much more efficient in keeping the MA and voltage relatively high. It's going to produce more energy for the same kV MA time settings. Okay, and this expresses that. It's what we've already seen. Just to refresh your memories here, that your that for oops that come back. Okay, that your single phase, your average kV and current is very close to the peak, as you see for three phase here, much closer to the peaks as compared to your single phase. That's what we've been talking about. Okay, so the heat generated when you go to three phase is a little bit more efficient, and you have to add those little coefficients. Okay, okay. Let's just say a little bit about capacities. One popular question is what modality produces the greatest heat? What modality requires X-ray tubes to have the greatest heat capacities? In CT scanning, by far, is the modality that demands tubes that can really take a beating. And they go up to 5 mega heat units, million heat units. That's a very high number. I remember years back when they announced that they were coming up with a 1 mega heat unit. Everybody looked at themselves and said, that can't be 1 million heat units. Well, now 1 million heat units is nothing. We can go to 5 and more. Interventionals are usually between 1, 2, or 3, somewhere in there. And your standard radiography fluoroscopy is more typically between 300 kilo heat units to maybe 600 kilo heat units. Occasionally you'll see a 1 mega heat unit, but usually you have to go above 1 to get to the high-end interventional and CT systems. Okay, there's one more chart, and we're getting very close to the end over here. One more chart. Let's talk about the so-called cooling charts. Okay, what this is all about, remember, is that we don't want to blow up the tube. And what we've just been looking at is what kind of exposures do we limit ourselves so that we don't blow up the tube. But now the question comes up, okay, I went through a particular series of shots. The tube is red hot. How long do I have to wait before I can expose again? This is where the cooling charts come in. How long does it take for tubes to cool off? Okay, and those charts look like this, somewhat different than what we've seen before. This time you're plotting heat units on the y-axis, and looking at the y-axis, the tube maximum heat units is always given at this peak value here. So this is your pretty much of a standard radiographic tube with a peak heat units of 300,000 heat units. Okay. The cooling curve is the one that's indicated with the red arrow, and it assumes, well, if you had 300,000 heat units at time 0, in other words, you just finished giving the maximum, the tube is about ready to blow up. It has its maximum heat stored on that anode. And what you do is you just, as time goes on, the tube is cooling off. How fast is it cooling off? That's what the cooling chart tells you. So for instance, if you started at 0 time at 300,000, the maximum, notice that after 1 minute, you're down to, looks like 220,000 heat units. And the question is, for instance, how long does it take to completely cool off? Well, to completely cool off to room temperature, that means 0 heat units. This particular tube will cool off in 8 minutes. 8 minutes. It went from, it's actually white hot, just about ready to melt off and explode, and yet 8 minutes later, it's at room temperature. Well, that's a testimony to how good our heat dissipation mechanisms are. These tubes can cool off relatively quickly, 8 minutes. Of course, if you have a patient on the table and you just gave the maximum, and now you got to hang around for 8 minutes before you come back to room temperature, that may be limiting. That's why for the high-end systems, interventional systems, you got to have much more than 300,000, so that you don't have to hang out waiting for the tube to recover. Here's an example. If you give 300,000 heat units, how long to cool off to room temperature? Well, I just did that for you, right? You start out at 300 and you end up at 8 minutes, where your the tube is back to room temperature, 0 heat units. Okay, 8 minus 0, 8 minutes. How about this one? What if you gave 140,000 heat units? How long to cool off to 40? Well, you start out at 140. Let's identify 140, where it crosses the curve. There's 140. And then you got to go to 40. Well, where is 40? There's 40. And so now you're going to go from 3 to 6.5, or putting it the other way around, 6.5 to 3. And that's an interval of 3.5 minutes. In other words, many times you don't wait to 0. Many times you haven't given the full maximum. These curves can be used for any interval of time at heat units. You can start at any heat units and finish off at any other heat units. Just get the difference between the 2 points, as we have just done on these examples. Okay. Finally, well, not quite finally, we've been looking at the tube charts, the tube cooling. How about the metal housing? How about the housing? I just want to point out a couple of ideas here and keep moving. First of all, look at the maximum heat capacity of the tube housing, 1.5 million. The anode was only 300,000, and but yet the housing is up to 1.5 million. So there's a lesson. Metal housings can take a much bigger beating than the anode. Anode is the weak point. That's where the maximum heat capacity is developed, and that's where you usually worry most about. And then, so lesson number 1 for the housing, it can take a lot more beating. Lesson number 2, notice how long it takes to cool off. Okay, the mechanisms for cooling off the overall housing is not as good as cooling off the anode. And I've given 2 possibilities, circulator and no circulator. What that means is the fan, the air circulating across the housing. It's pretty efficient. Notice that if you have a circulator, a little fan, you cut the time of the housing to cool off to room temperature by half. No circulator, 150 minutes. Circulator, 75. Don't have to remember the numbers. But again, I want to emphasize the concept and the idea, or the lesson. Lesson number 1 was housings get a lot more beating and can still keep themselves together. The number 2, it takes a long time for the housings to cool off. And those are the 2 main lessons. And now the final curves that you see on these charts is your fluoroscopy buildup. Okay, we have to address fluoroscopy. You know that you press the pedal and you see an image, but as your foot stays on the pedal, it builds up heat. This is what these curves represent. the ones that start at 0 and build up. And they're the fluoro build-up curves. And they tell you, as you step on the pedal with time, how does the energy build up? How do the heat units build up at the anode? And how they build up depends on the voltage and MA that you are operating at. It depends on the heat units per second. Uh, so for instance, you have a curve here at 200 heat units per second. Yeah, way up at the top, you got a curve at 1400 heat units per second. What is a heat unit per second? I'll leave this, you can look at this on the recordings, but skipping the math, get to the bottom line. The heat units is just the product of the voltage and the current. Every time you step on the pedal, you will have a certain voltage, you will have a certain MA. And the amount of heat that you build up depends on the product of the two. And the value or the magnitude of those two numbers, kV and MA, depends on your patient. If you have a real big patient, the machine will seek a high kV and a high MA, therefore producing more heat units per second. You have a thin patient, the machine will, in automatic mode, will seek a lower kV and a lower MA, and therefore you produce less heat units per second. So heat units per second, how much voltage are you operating at? How much MA are you operating at? Okay, this slide summarizes what I just mentioned, and every machine will seek an equilibrium technique depending on the how thick and how dense the patient is, and that then defines the heat buildup. Okay, and let's ask the question: is the heat capacity of the tube ever exceeded? In a very extensive procedure where you have your foot on the pedal for extended periods of time, have you ever wondered, gee, am I going to blow up this tube? How do you figure that out? That's where these charts come in. For instance, as an example, if I was operating 100 kV and 2 MA, I've noticed that in general, fluoroscopy operates at relatively low MAs, a half to 2 MA. If you're wondering what MA or kV your machine is equilibrated to for a given patient, just ask the tech. It's listed, it's shown on the screen back at the control station. But in any case, if you had 100 kV and 2 MA, how long would it take? How long can you step on the pedal and not worry about the tube blowing up? Okay, exceeding the rating. Well, remember, heat units per second is the kVp times the MA. 100 times 2 is 200. So now you're looking at the 200 heat units per second curve. That's way down here. And by the way, this is a pretty much a typical patient value. And what this is telling you is that you can step on the pedal and notice that that curve never gets to the maximum. The maximum is 300,000. So you're never anywhere near 300,000. In other words, at that setting, your heat dissipation dissipates the heat to the point that there is no more heat beyond 40,000. The tube will get hot, but it'll never exceed more than 40,000 as long as you're at these settings. So, tube essentially will never blow up. Okay. How about on the other hand, if you had 140 kV, that's an unusually high voltage. Usually fluoroscopy is not done beyond 120, and the 10 MA in this example, typically you are, as we said, down at the half to 2 MA, at most 3 MA. So 140 kV at 10 MA is exceedingly high. What if we ask the question, how long before exceeding the rating? Well, again, the heat units per second is the product of the kV and the MA. That'll be 140 times 10. That's 1,400. And if it's 1,400, that's that top curve. So as soon as you stop, you start pressing the pedal, up it goes, up it goes, up it goes, up it goes, and notice that it reaches the maximum, in this case the 300,000 that on that tube. It reaches its maximum after 8 minutes. 8 minutes. So at that point, beyond that point, you are in trouble. if you continue pressing the pedal. In reality, what the engineers do for us is they lock out the machine. They lock out the machine so that you cannot access 140 kV and you cannot access 10 MA, so that you are locked out of particular technique factors because of the possibility that you would blow up the tube. Okay, so if the engineers do their job well and locking the tube out safely, then you typically don't have to worry about blowing up tubes. It has happened. It has happened, but typically, in your experience, you've probably never seen it happen to yourself or or heard of anyone else going through that. I have on occasions, but they're relatively rare. Okay, that's the end of chapter 3. I've put some summary things over here, going right back to the beginning of the chapter where we have X-rays produced when electrons, high energy electrons, impact the target. Remember that? And we talked about different targets, typically tungsten for radiography, fluoroscopy, CT, molybdenum rhodium for mammography. There were some trends for going back to tungsten, as we discussed, for your digital mammography. The mechanisms of X-ray production, Bremsstrahlung and characteristic radiation, and we saw that Bremsstrahlung dominates for tungsten targets, while a characteristic radiation dominates for mammographic energies and molybdenum rhodium targets. Okay, various other details here. I'll let you look at the recordings that we covered. Okay, and then finally, concerning the heat capacities of these systems, we mentioned that most of the heat goes into most of the energy of the electrons goes into heat production. Look at that, more than 99.5%, and in some cases even 99.9% of the energy goes into heat, and a very small fraction into X-rays, actual useful image-producing X-rays. But we have various heat dissipation mechanisms available to control that heat. Otherwise, it would really be very difficult to avoid blowing up that X-ray tube. And the last thing we just looked at, was these heat loading and cooling charts. Okay, well, that should do it. Let's go on to the next chapter, and chapter 4. Here we go. Okay, chapter 4. Chapter 4 talks a little bit more about the electric basics and voltage generation, and it's probably the most boring of all our chapters, I'm afraid to say, but I've added some additional information that may make it a little bit less boring, but it's a lot of the electrical generation is more of a concern for the engineers rather than for us, for radiologists or even for physicists. But the premise is we have to power X-ray machines, and the question is how. We have to power magnetic fields in MRI. We have to power the ultrasound units. Okay, we need electricity, and let's take a look at some of the electrical basics. This goes back to some definitions we had already made. I won't dwell on it. The electric current concept is whenever you have electrons moving per unit time, you have electricity. The unit of electricity is the ampere. 1 amp, abbreviation of ampere, is 1 coulomb per second. A coulomb is a unit of charge. So much charge, electronic charge, moving per unit time, second. And don't have to remember the actual value of the electrons, but it's a huge number of electrons, a huge amount of charge that for 1 ampere would be moving down, per unit time. And what gets an electron to move? An electric voltage. Okay, it's that which gets electrons to move. That's what a voltage is. And how does it do that? It has negative charge on one end and it has positive charge on the other end, so that an electron will be repelled by the negative charge and flow toward the positive. And once an electron flows, you have current. And the unit of electrical voltage is the volt. These are the component units. Notice energy per unit charge. It's talking about, well, if you're going to move an electron moving has kinetic energy. How much energy does it have? 1 volt will give an amount of a charge of a coulomb, 1 joule. So many electrons will end up with so much energy, joule per coulomb. Okay, there's your voltage. One region negative, one region positive. And when you have that voltage, we've already seen that electrons will flow from one end to the other end, from negative to positive. Okay, this can happen in space, just a vacuum. It can happen in a gas, and it can happen inside of a wire. Wherever you have electrons that are able to move under a voltage, the electron will move. And the example over here is very similar to what's going on with X-ray production, where you accelerate an electron, and imparted energy to it, and then harvested that energy in the form of X-rays. Well, let's look at some of the basics of electricity and magnetism, electromagnetism and electromagnetic induction. Let's look at electromagnetism. What does that tell us? It tells us, as shown in this slide, that if you have a current given by the yellow arrow here, as an electron flows through space, whether it's space or in a wire, there'll be a magnetic field around that wire. There'll be a magnetic field around the wire. Any electron moving always has a magnetic field around it. Okay, and if you have a linear flow of electrons, of current flow, then you'll have a circular magnetic field. Okay, but the concept is electricity creates magnetism. Hey, if you ever wondered how did you get that big magnetic field in an MRI unit, this is telling you, pass a current and get a magnetic field. This is where we're going. I'll illustrate that as we go along. What if instead of a linear flow, you had flow in a loop, as shown here? So now your current yellow loop, but now you have a magnetic field, but now you have it right down the middle of the loop. The magnetic field is the green arrow. And when you have a circular current, you have a linear magnetic field, that green line. Okay, wherever you have current flow, whether it's moving in a line or moving in a circle, you always have a magnetic field associated with it. Okay, let's look at that a little further. If instead of one loop, what if you had many loops? In other words, what if you have a coil? This is a picture of a coil. It has a voltage across the coil, V, and there's going to be a current through that coil. And now, as we saw, and we've established, whenever you have a current flow, you have a magnetic field. But this is the way the magnetic field will appear. It's as if you had a bar magnet with a north and a south pole, and now you have a magnetic a field around that bar magnet. Again, this is same ideas of electromagnetism. Electromagnetism says, given electricity, a magnetic field will result. Okay. Well, so what? What's the importance of this? The importance of being able to produce a magnetic field. Well, the greatest, more obvious applications would be in MR. In MR, we need magnetic fields. We need the main field, magnetic field, to produce the B0 field, like, for instance, a 1.5 Tesla or a 3 Tesla unit. How do we get those Teslas? Teslas, by the way, are a unit of magnetic field intensity. You get them by having coils and passing current through the coils to produce those fields. And we have those coils in a cryogenic environment, in a superconducting state, so that your current gets very high values, and if they get very high values, you're going to get very high values of magnetic fields. Magnetic fields go up as your current goes up. I've also listed 3 other areas where we use coils. The next most likely one that you've come across is the so-called RF coils. Those are your head coils. Those are your body coils. Those are your surface local coils. Their role is to excite and detect the MR relaxation process. But those are coils. You pass a current through those coils, you get a magnetic field. Then you put that magnetic field to work. In this case, to excite the various tissues and to detect as those tissues relax. There are other coils. The next most popular coil or most common coil you hear talked about is the gradient coils. Those are for spatial localization, to be able to detect where are the signals coming from within the body. You can generate a signal, the signal that constitutes the relaxation signal of various tissues, but now you have to know where they come from within the body. That's the role of the gradient coils for spatial localization. And you need 3 of them, X, Y, and Z. The way you localize in 3-dimensional spaces, you got to get the 3 coordinates of 3-dimensional space, X, Y, and Z. We need 3 gradient coils. The ones that you hear least about are the shim coils. Those are coils that are used to produce homogeneity. The image quality is going to depend critically on how homogeneous the field is, and the way we tweak the field is with these so-called shim coils. A lot of more to be said about these coils, which we'll say when we get to MR imaging, but just for now to establish that this whole idea of electromagnetism is just more than a cute idea in a physics book. It is the basis for MR imaging. This is how we get our magnetic fields to do particular functions, as these 4 functions that I've just mentioned as an example. Here's a cutaway view of an MRI scanner just to show you where some of these coils are located. And the RF coil, this would be the body coil. You can't see the body coil. It's usually part of the gantry, but you have seen the head coil, which you roll over the patient's head, or various surface coils that you place in various parts of the anatomy of the patient. The gradient coils, and then the main field coils that go completely around the patient. So you have these loop. Remember the loop? You have a loop, and then you have magnetic field going right down the center of the loop. Remember that picture? The typical magnetic fields, the north and the south, go from head to toe on the patient. They go right down the middle of the bore of a superconducting system. Okay, so you don't see the shim coils in this setup over here, but they are located in various points within the gantry to help homogenize the magnetic field at the various points within the gantry. Okay. Well, this is what it would look like without the pretty the pretty facing. Head coils, some foot coils, hand coils, whatnot. Here's the gradient coils. The gradient coils are the ones, for instance, with the green, the blue, and the red, various configurations. Why those particular configurations? Hey, we'll talk about that when we get to MRI. I just want to, again, as we mentioned, I just want to show you the importance of coils and the importance of the concept of electromagnetism. Okay? How about electromagnetic induction? Electromagnetic induction, what importance does that have in radiology? The idea there is when we operate an X-ray tube, we want to go up to over 100,000 volts, right? How do we get 100,000 volts? What's available coming out of the wall is 110 volts. 110, not 110,000. How do you go from a low voltage to a high voltage? And also there are situations where you may want to go to a low voltage. You start out with 110 coming out of the wall, but you want to charge your computer, or you want to charge your telephone. They operate at much lower voltages. Uh, uh, every time you go to charge a device, notice that you need an adapter, and there's always a little black box that comes along with it. That little black box is based on, uh, is what we call uh, a transformer, and it's based on the idea of electromagnetic induction. So let's see what that concept is. You have a coil, okay? We call it a primary coil. It's fed by the line, alternating current coming right out of the wall. And there's our little coil. And of course, when you have a coil, you're going to have a magnetic field. And if the current is changing all the time, that's what alternating current does, then you have an alternating magnetic field, a changing magnetic field. Sometimes the top is north, sometimes the top is south. It keeps flipping back and forth because the current that feeds it is flipping back and forth. And now we put another coil, a secondary coil, given by the letter S, a secondary coil nearby, so that the changing magnetic field of the first coil, the primary coil, cuts across the secondary coil. And now electromagnetic induction. Magnetic fields produce electricity. See, we just finished electromagnetism that said electricity produces magnetism. Now we're saying magnetism produces electricity. There'll be an electric current. There'll be an electric voltage in the secondary coil. That's the idea of electromagnetic induction. I'll repeat, and both ideas. The first concept that we looked at was electromagnetism, that said electricity produces magnetism. And now that very magnetism that we're going to produce with the electricity, we can induce a voltage, we can induce electricity in a secondary coil, because the changing magnetic field of the first coil induces voltage in the secondary coil. That's electromagnetic induction. Changing magnetic fields create electricity. Well, so what? What are the applications? I mentioned that you would like to take a voltage, a relatively low voltage, I mentioned 110 volts coming out of the line, and we want to make it up to over 100,000 volts. How do you do that? You do that with a transformer. Now, you know that out of the wall, from the power company, we can also get 220. And in fact, we could get 440. Typically, our X-ray tubes are generated out of the 440. It's a special line that the power company does supply, and you feed that 440 volts into the transformer, and what comes out of the transformer? Over 100,000 volts. That's what a transformer does, or one of the things it can do. It can increase the voltage to the desired values, or, notice in parentheses, it can decrease the voltage to a desired value. It can convert to low or high voltage. When it converts from low to high, we call that a step-up transformer. That's how we get our high voltage. When we convert from high to low, that's a step-down transformer. I gave you the examples of adapter plugs to charge your phones and your computers. But in radiology, to power a filament, to get your thermionic emission, to heat up a filament in an X-ray tube, that doesn't take 110 volts. That takes more like between 6 to 10 volts, not 110. So you got to power down the voltage out of the wall down to the levels that are used to power your filaments. Let's take a look at how a step-up transformer works. How do you go from low to high? Okay, to go from low to high, you just have your primary windings with a certain number of turns, And then if you want to go to higher voltage, you want to step up, then the secondary windings have to have a greater number of windings, and it's directly proportional. You want to double the voltage, then you need double the number of windings in the secondary. Okay, simple as that. And here is a complete setup with the terminology, the current and the voltage primary, the current and the voltage secondary, and for a step-up transformer where I've shown more, come back, where I show more turns in the secondary for a step-up. Now it works in the opposite direction as well. If you want a step-down transformer, you go down in coils, in number of turns in the coil. So if you cut the turns in half, you will cut the voltage in half. Okay? So they go in a proportion, whether you're step up or step down. There's an actual little expression. I don't think they'll give you that expression on the boards, but just to show you where I mentioned the direct proportionality, this is what you see in these ratios, and it's just the ratio of the turns equals the ratio of the voltages. That's your transformer law. The ratio of the turns equals the ratio of the voltages. Okay? The ratio of the turns sometimes is called, it's pretty much always called, the turns ratio of the turns. And and notice that the change in the turns ratio equals the change in the secondary. So that's where that proportionality comes in. I double the turns ratio, meaning I double the number of turns in the secondary. I get double the voltage. Okay. Here's a quick example. Let's say you had 1,000 turns in the primary and 1,000,000 turns in the secondary, and you came in with 100 volts. Well, what would be the voltage that you would produce? The turns ratio is 1,000,000 over 1. That's 1,000. There's your answer. You would have 1,000 times more volts. So if you start out with 100, 1,000 times 100 is 100,000, or just 100,000, 100 kV. We just got over 100,000 volts, but we started out with only 100. That's what the transformer does for us. Okay, and this is just a little, this is the rule of thumb that I use, just using the turns ratio. Here, you actually do the calculation from nitty gritty. For our purposes, you're not going to do nitty gritty calculations. That's what the board people said. Just go by the concept. Double the turns ratio, double the voltage. Okay, moving on. Is this something for nothing? You start out with 100 volts and now you got 100,000. Sounds like something for nothing, right? Well, what happens is you never get something for nothing. What you go up in voltage, you lose in current. So if you double the voltage, you'll get half the current. So you're back to total energy that you began with. You haven't created anything revolutionary new over here. Okay, so and if the volts go up by 1,000, then the current goes down by 1,000 to compensate. Okay, and this is the expression. It's the notice that the S is on top for the turns, and the S was on top for the voltage, but when it comes to current, it's reversed, it's inverted. Okay, well, I'm not, our time is running short. Here's an example of the current to show you that if you go from 1,000 turns to 1,000,000 turns, you went up by a factor of 1,000, you're going to go down by a factor of 1,000. So 10 divided by 1,000 comes down to 10 milliamps. Okay, you can do the math on your own. Okay, but notice it's 1,000 factors down because the voltage went up by a factor. Okay, let's just, I'll just lay that out. I'm not going to go through the math. This is just going through the nitty-gritty math. But let's finish up with the idea of a step-down transformer. Now time is up, but it's the same idea, but now we're going in the opposite direction. In this particular example, notice that you went, the turns ratio you start out with 1,000, but then you went down to 100. In other words, a factor of 10. Well, if you have a voltage of 100, you got to go down by a factor of 10, and there's the answer, 10 volts. Okay, so the same idea, except that you're going in the opposite direction. And I mentioned that the step up is for the high voltage production. The step down is for the filament supply, where you're only going down to, you take the wall voltage and you got to get down to 5 or 10 volts. Okay, this is the last thing I'll say, and then we'll cut it short, and I'll continue the next time. Another application of a step-down transformer is in the high voltage selection. The high voltage selection, where you want to go in very small incremental changes. I'll say a little bit more about auto transformer the next time, but let's stop at this point. And if you have any questions, we'll entertain those at this time. If not, you will have a good day. Kick around the possibility of my being in person on December 19th. I'll be in town for that. Okay, have a good day. Bye-bye.
Thank you. Thank you.